Welcome to day one of our 10-day AP Chemistry review. Today, we are diving into atomic structure and periodic trends, the foundation of modern chemistry. If you've ever wondered about how we know what's inside of an atom and why elements behave the way they do, this is the perfect place to start. Now let's get into it. So this is the periodic table. The we have total about 120 elements. It is well structured into this periodic table. We have groups and periods. So we have period 1, 2, we have total 7 periods. 7 periods, 1, 2, 3, up to 7 periods. We have total 1 to 18 groups. More importantly, it is important to main group, which is 2A, 1A, 2A, and here 3A, 4A, and so on and so forth up to 8A. 8A is called main group. The group 8A is called the noble gases, which has stable electron configuration called the octet. So let's revisit the structure of an atom. So atom has nucleus and outside of nucleus. Nucleus is embedded very like core of an atom and taking very small region called nucleus, very dense, 99.99% more than that of mass of atoms is residing upon this nucleus. Nucleus contains protons and neutrons, and vast majority of space is occupied by electrons. It is very important to know the subatomic particles. There are three subatomic particles. From top, protons, and neutrons and electrons. And most important one is their charges and mass. The subatomic particle and microscopic their interactions, chemical reactions are determined by the charges. Same charges repel each other, different charges attract to each other. So we need to know the charge. The unit charge is carried by a proton and a neutron, an electron. Proton carries +1 charge, electron carry -1 charge. The magnitude charge is the same but opposite. Neutrons carry, by the way, 0 charge. So neutron doesn't contribute at all to the charges, but the relative mass is important. Protons and neutrons have about the same mass, 1 AMU, up to 3 sig figs. They have the same number of sig figs. At the fourth sig figs, they are slightly different. They are heavy particles, but electrons have about 1/1800 AMU. So relatively speaking, compared to the mass of protons and neutrons, mass of electrons is negligibly small. Now let's think about isotopes. Iso is derived from a Greek etymology meaning same but different. So atoms of the same element, same meaning it has the same number of protons. When the number of protons is different, it is not the same element. For example, when you say carbon, all of the carbon isotopes have 6 protons. When the number of protons is 7, it is nitrogen, not carbon at all. So they have the same number of protons but different number of neutrons. For example, carbon has many isotopes, but majority of them is carbon 12 and carbon 14. So let's compare these two isotopes. Carbon 12 and carbon 14, both of them, they are carbons, meaning they have same number of protons, but different number of neutrons. So this is the diagram that represent the nuclei of carbon isotopes. Carbon 12, carbon 14, they all have 6 protons. 1, 2, 3, 4, 5, 6. 6 protons right there. But number of neutrons, carbon 12 have only 6 neutrons, but carbon 14 has 8 neutrons. So their number of neutrons different, their mass is different. But because their number of protons, the number of electrons are all same, their chemical properties are exactly same. The only difference is their mass. So then atomic mass is weighted average of all the isotopes. So let's see the formula. Atomic mass is fractional abundance. Each of isotopes has different natural abundance found in nature, and each of them has different mass. So let's multiply this one and add up everything. That is how we calculate the weighted average method. So here fractional abundance is natural abundance divided by 100, and isotope mass is given. This is all churned out by mass spectrometer. When you collect certain atom, certain elements, and then plugging into this mass spectrometer, this is churning out those data, isotope mass, and then its natural abundances. Let's see example. Chlorine. Chlorine is very important halogen, has two naturally occurring isotopes, chlorine 35, chlorine 37. The mass is very close to its mass number, 35, 37, but they are all fractional number. And their natural abundance is 76% and 24%. Now let's plug into that expression. Let's multiply the fractional natural abundance times its mass, fractional natural abundance times mass, and add up. And then we are ending up with 35.45 AMU. So when you look at the periodic table, we see chlorine has 17 protons. So all of chlorine atoms have, chlorine isotopes have 17 protons, but its atomic mass is 35.45 AMU. And this average mass is calculated by this equation. Now let's look at the ions. Ions are very important. For example, ionic compounds are composed of ions and their attraction between different charges. We call this a Coulombic interaction, and complete each ionization equation as shown below. First, let's look at magnesium. Magnesium is a metal, but let's make it into sublimation process, make it into gas. Then magnesium is readily losing 2 electrons. Magnesium has neon core, magnesium total 12 electrons. So this one has neon core and 3 has 2 electrons in its valence shell. So it is readily losing these 2 electrons in its valence shell and making 2 plus charges. Remember, magnesium belongs to group 2A. All those group 2A elements, including magnesium, calcium, strontium, and barium, they are readily losing 2 electrons and gaining 2 plus charges. Now let's look at sulfur. Sulfur belongs to group 6A. It is very close to the octet. It gains 2 more electrons than it is not. It has 8 valence electrons. So sulfur is gaining 2 electrons, becoming as 2 negative anion. Aluminum has 3. Aluminum has 13 total protons, 13 electrons. It belongs to group 3A. It has 3 valence electrons. Aluminum has also neon core and 3 has 2 and 3p1 electron configuration. So total 3 valence electrons. So it is losing 3 electrons, becoming aluminum 3 plus. When you look at this electron, you need to think about charge balance. The left hand side total number of charge and right hand side total amount of charge should be equal. In this case, neutral left hand side and neutral right hand side. And because electron carry -1 charge, either cations, and those aluminum 3 plus, those are metals, metal cations. Remember the trend. The metals have tendency of losing electrons. Non-metals have tendency of gaining electrons. So this ionic equation show the relative trends. Now let's see how to write electron configuration. For example, hydrogen, the electron configuration is 1s1. 1s meaning orbital, and subshell, in 1s subshell, it has only 1 electrons. And here is helium, electron configuration 1s2. In 1s subshell, 1s orbital, it has 2 electrons. And the 2 electrons has spins. We have up spin and down spin, and should be opposite side. Same spin is prohibited. This one is prohibited, or down spin prohibited. Should be up spin and down spin. And we have, like, usually 4 subshells are used to describe electron configurations. S, P, D, F subshell. S has only 1 orbital. This is number of orbitals. S has 1 orbital, P has 3 orbitals, D subshell has 5 orbitals, F has 7 orbitals. Each orbital, the maximum number of electrons is 2. So then in S subshell, 2 electrons maximum, P 6, D 10, F 14 electrons maximum. Now let's look at electron configurations in detail. Silicon has 14 electrons. So it is 1s2 filled up, then 2s and 2p subshell filled up, and 3s2, 3p2. So total 14 electrons. Here the 1 and 2, they are co-electrons. 3 those principal subshell number, those are valence electrons. So we can write this one in abbreviated electron configuration like neon core and 3s2 and 3p2. And we have 4 valence electrons like this way. So when you write the electron configuration, it is very helpful using the periodic table as a guide. And period number and working with S block. The left two columns of the period table is called S block. The right hand side 6 columns called P block, and the middle 10 columns called D block. Bottom lanthanize, actinize, it is called F block. So we are filling up 1s and 1s2, 2s and 2s2, 3, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3sp, p2, p3, p4, p5, p6, 4s1, 4s2. Follow this order, and 3d 1, 2, 3. And here is exception. Here is chromium, here is copper, and they have exceptions. This one has argon core and 4s2, but 3d1. 3d4, this is regular. When you write the order should be the regular like this way, but this exception, it is 1 electron for 4s is excited to a 3d subshell, making 5, because half-filled electrons are more stable, and same as copper. Copper has now argon core, and 4s1, 3d9, 3d10. So then fully filled, this subshell is also stable, so it is exciting 1 electron from 4s subshell to 3d. Now let's look at a free response problems and multiple choice problems. And first before going to that, let's look at periodic trends. Electron configuration is very useful, and there is an exploratory power for the number of valence electrons, trends in ionic size, atomic size, ionization energy, and metallic character. And let's look at group number and valence electrons. Group number of main group elements, their groups are 1A, 2A, 3A, 4A, so on and so forth up to 8A. They are very useful to predict the number of valence electrons for the elements in that group. For example, group 5A, from top to bottom, period 2 nitrogen, phosphorus, and arsenic, antimony, and bismuth in this order. They have similar characteristics. Why? Because their number of valence electrons are the same, 5 valence electrons. So this number before group A telling us number of valence electrons. Now let's go into the periodic trends. First, atomic size or radius is increasing from left hand side to the right hand side in the same period. From the right hand side to the left hand side, so increases like this way, because number of protons increase from left hand side, right hand side. So then the size is getting smaller when you go from left to right. So then from right to left, it is increasing. And from top to bottom, the principal shells increasing from 2 to 3, 2s to 3s, 3s to 4s, 4s to 5s. The shape is same, but the size is increasing. From when the shell is increasing, the size increasing. So then, relatively speaking, diagonally down from top right hand side corner to the bottom left hand side corner, size is increasing. And metallic character increase, we know that this one is metalloid. We have non-metals right there, non-metal and non-metal. And here we have metals. So then from non-metal side to the metals, the metallic character increases. The tendency of losing electrons, those metallic character is increasing. And next one, ionization energy. Remember, metals have tendency of losing electrons. Tendency, it has tendency of losing electrons. Tendency of losing electrons. So we are using small amount of energy to take electron away from metals. Non-metals have different tendencies. They have tendency of gaining electrons. So it takes large amount of energy to take electrons, making positive charged ion. So it takes more energy. So ionization energy is increasing from left hand side down corner to the right hand side up corner. Now let's look at multiple choice problems. Which element has the highest ionization energy? Sodium belongs to group 1A, alkali metal, readily losing electrons, very reactive in losing electrons. Magnesium belongs to group 2A, two valence electrons. It is also reactive, not as much as sodium, but still reactive. Chlorine has group 7A. Chlorine has 7 valence electrons. It wants to gain electrons to have the octet, 8 valence electrons. Argon group 8A, it is complete octet, currently very stable with 8 valence electrons. So when we take one electron and let's say argon becoming argon plus, and when you take one electron, the ionization energy is very high because this is octet and this one is unstable. We are taking stable octet into unstable argon plus. So this take the amount is very large. So answer is 4. Now let's look at practice problem. Photoelectron spectroscopy. Let's see two problems. First, 2019 free response number 5. Photoelectron spectrum of an element is represented above. Write the ground state, electron configuration of the element, and identify the element. Here, let's look at what is on the x-axis, what is on the y-axis. What is on the x-axis is the binding energy of per electron. As it is strongly bound, then the electrons are more core electrons deeply embedded. And on the right hand side, on the y-axis, we have relative number of electrons. So here, the binding energy increasing from right hand side to the left hand side. So they are 10 to negative 18, so same. It is 647, 70, and 7 and 0.9, which is about 1. And then so we see that here the electrons on the left hand side must be core electrons because it is high binding energy. This one must be valence electron. Okay, now let's get started. Here this one must be 1s. In 1s subshell we have only 2 electrons. 2s, 2 electrons, and 2p, 6 electrons. That's why the peak is 6 times. I mean 3 times. 1, 2, 3 times. 2 times 3, 6 electrons right there. Next one is 3s, 2, and 3p, 6. Next one must be 4s, 2, because the height is same as this one, and it must have 2 electrons. So then electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, which is up to argon core and 4s2. So this is electron configuration of calcium, total 20 electrons. Now calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of the atom of the element. So this is the valence shell. Valence shell 4s2. And let's look at the value. 0.98 times 10 to negative 18 joules of energy is required to take this one away. So then energy of photon must be at least 0.980 times 10 to the negative 18 joules. Then knock this electron out and then eliminate this one, making to like leaving the metal. Leaving this material. So then energy is h nu, which is hc over lambda. Planck constant and speed of light is same constant. This one must be bigger than 0.980 times 10 to the negative 18 joules. So when you look at this one, lambda must be smaller than hc over 0.980 times 10 to the negative 18 joules. When you plug in Planck constant 6.626 times 10 to the negative 34 joules times second, and speed of light 3.00 times 10 to the 8 meters per second, the answer is 202 nanometers. So lambda must be less than 202 nanometers. Remember, visible light has 400 nanometers to 750 nanometers range, and 202 is less than 400 nanometers, so this is UV light. So we need to irradiate UV light of 202 nanometers or less than 202 nanometers, knock it out, these valence electrons, knock valence electron from the valence shell. Now let's look at another example of those electron spectroscopy, photoelectron spectroscopy problem. Let's look at 2021 free response problem number 2. The mass spectrum of a pure sample of silicon is given right there. So then once you do this one, given this one, let's go to the period table first. Let's find out the information of silicon. Silicon has 14 protons, 14 electrons, and it has 28.09 AMU of mass. Okay. How many proton and how many neutrons are in the nucleus of an atom of the most abundant isotope of silicon? So silicon has silicon 28, silicon 29, silicon 30 right there. And their relative abundance is the y-axis. So definitely this one is the most abundant. Clearly, this is the most abundant. Their mass is 28. Actually, the mass is not 28, 27.999 is something, but close enough to 28. And this one, silicon has 14 protons. And then the mass of this one is 14 protons plus amount of number of neutrons. The mass is about equal to 28 AMU. Remember, each proton has about 1 AMU, so this one is 14 plus x is equal to 28. So x is equal to 28 minus 14, which is 14 AMU. Because each mass of neutron has about 1 AMU, we know that this one has now 14 neutrons. So 14 neutrons. Write the ground state electron configuration of silicon. Silicon belongs to group 4A, right below carbon. So this one has neon core and 3s2, 3p2, and which is 1s2, 2s2, 2p6, and it is filling up the subshell, and in the valence shell it has 3s2 and 3p2. And based upon this information, now let's look at its the photoelectron spectrum. So this is the photoelectron spectrum. Now remember, this one is more like this one is core electrons, and this is the valence shell, because the energy, relative binding energy, megajoules per mole, is now left hand side is large value, right hand side smaller value. Okay, so then we already know the electron configuration of silicon. Silicon has 1s2, 2s2, 2p6, and 3s2, 3p2. So this one must be 1s2, and this one must be 2s2. This is 2p6, and 3s2 is right there. It says 2p subshell must be right below. I'm right beside it. This one must be 3s2, 3p2. The height, the energy is requiring to take this 3p electrons slightly smaller, so it is on the right hand side. And the height must be the same because we have 2 electrons right there, 2 electrons right there. So they make the height the same. It is right neighboring to the right hand side. Okay, so this is concluding day 1 of our 10-day AP exam preparation. And today we have takeaways. First, we were able to understand subatomic particles and ion formation. Remember, there are 3 subatomic particles: protons, neutrons, electrons. And protons and neutrons are embedded deeply into the atom. At the core of atom, very small and dense region called the nucleus. And the proton has about 1 AMU of mass, positive charge. Neutrons, 0 charge, but has also 1 AMU of mass, approximately. Electrons has negative 1 charge, but it is very light, 1/1800 AMU, negligible small mass. So we have to also draw electron configurations and orbital filling, and periodic trends, the size and metallic character, and its first ionization energy, and why they occur that way. We are able to practice interpretation of photoelectron spectrum graph, 2019 free response 5 and 2021 free response 2. So in day 2, this one is conclusion of day 1. Day 2 will be reviewing bonding and molecular structure, including how to draw and interpret Lewis structure, resonance structures, and lattice energies. Thank you everyone for watching this video. I hope to see you in the next video.